well, some modelling that we've been doing of subduction zones, trying to understand what happens when they try to ingest material, and sort of comparing what happens with straightforward regular subduction and what happens when they're trying to kind of swallow stuff. Okay, I went to Wikipedia. This comes from part of the exercise that was conducted at CIDA, which was to actually update Wikipedia so that it made sense with some of the things that we were sort of complaining about. But nonetheless, there is a sort of a traditional view of a subduction zone, and basically it can all be summed up by the fact that we draw everything in cross sections. Okay, and that when we look at what happens when something is swallowed by a subduction zone, the cartoons typically look like this, which is that it's two-dimensional, and the only interesting dimensions are these two in vertical cross section. But working on this problem started with us quite some time ago. Looking at, when you look at a subduction zone, of course, it's far from two-dimensional in the sense that, sure, it has, it's longer than its y, but there's a lot of variation along strike, and a lot of that variation occurs. Well, you can see that a lot of sort of variation occurs because of the interference of buoyant material with the subduction zone itself. So if we kind of zoom into these spots here, this is the sort of this is the point we started doing this work in the first place for Wendy Mason's honours thesis 10 years ago, looking at the Ogasawara Plateau. And the reason we chose that was because there was some good tomography showing what was sort of happening to this plateau as it was being subducted. But there are plenty of places you can look to see bathymetric highs basically being subducted, and they seem to do something odd to the subduction zone. And I guess my argument with this sort of my discussion point is that the result of this behavior is that you have to think outside the original two-dimensional box and move to 3 dimensions and think about things in that zone. So some very simple, to introduce you, if you like, to what we are simple models. So it's kind of a Zen problem of what one plate subducting looks like, but it's kind of an interesting trial problem. That a plate that's sort of being subducted into the interior, but no overriding plate, is kind of the archetype for the original analog experiments. What people did to try to understand what are sort of the dynamics of a downgoing plate. So we spent some time using those analog experiments actually as benchmarks for the underworld code. And it's probably not appropriate to call them benchmarks, but we tried to apply our numerical models to the models of Wouter Scheller, who had started doing those at Monash for his PhD, and it looked like it was something very, very simple sort of experiments that we should be able to reproduce. So we did a lot of those, and then we decided to see what would happen if we introduced anomalous buoyancy, if you like, into that system. So this is a numerical experiment viewed in plan view. There's a trench that starts out at this point here, where this line is, this faint grey line here, and a buoyant sort of plateau that comes swept into that trench by the action of subduction itself. And this is not a detailed analysis of that experiment. There's a mirror here, in fact, in this kind of setup. So there's no slab edge there, but there is one here. So the idea is just to look at what happens when something gets swept in, not necessarily in the symmetry plane. So what does happen? Well, if I can just interpret these models for you, these are for all different kinds of plateau buoyancies and thicknesses and all kinds of other things like that, and different parameters of the subducting slab. But basically, what happens is that local to the place where subduction is being sort of congested by this plateau, there is trench advance. Everywhere else there is at least a little bit of retreat. And here where there's a slab edge, there's very dramatic retreat. Relatively speaking, there's, relative to this point, if you like, there's quite a lot of retreating going on. And that's really what the observation of these experiments were in detail. I don't think they were sophisticated enough to say much more. So we can talk about these in terms of buoyant material sort of embedded near the surface of the plate. Some other experiments which I'll probably just, I won't dwell on, but these were led by Pete Betts. We're looking at what happens if you have buoyancy underneath the subducting plate. So those two sets of experiments sort of, I'll sort of touch upon. So, well, there are lots of places. The story itself comes from sort of the benchmarking part of this comes, interestingly enough, from looking at Southeast Australia. And I already pointed out to you what happened, where we started this looking at the Isobonin system. The other place that we've been quite interested in, which we've seen a little bit of today, is the current sort of ongoing collision, subduction, accretion of the Yakutat Plateau. Well, terrain, no one necessarily tells you there's a plateau. But anyway, there is this collision zone going on up here. So we can look to those as being sort of, we can look to some examples around the world and try to discuss, what do we know about subduction today and how does it behave dynamically, and try to look back at some of the questions that I guess I was hearing this morning about how do we sort of go back in time and try to work out the relationship between sort of the geological system and what the subduction zone was doing at the time. So my original point was that thinking of problems in two dimensions is at the very least misleading. And I show you this example. Here's a tiny little piece of a buoyancy anomaly in here. And there's a sort of a cross section taken through there. So both of the two-dimensional choices sort of represented. We can look at the plan form, but we can also look at the cross sections. And these are approximately scaled from the beginning of the experiment. So sort of that number there is 30 million years or something, and this is about 80. So sort of 50 million years of model time. And during that time, the little plateau starts out here somewhere, and collision occurs around here. There's some subtle blends of orange in here that you won't be able to see with this projector. But a certain amount of this plateau is scraped off and properly subducted. A certain amount so that's scraped off the bottom of the plateau itself. A certain amount is actually sort of accreted onto the side here, and a certain amount of it is sort of under thrust. At some point, the subduction zone gets going again, and you have a little piece of the original plateau crust now on the overriding plate. You also have some of it which has disappeared and is down here. And I recommend looking at those original figures. It's not as much orange upon orange in the original figures, but the movie tells a different story. Well, it's the same story from a different point of view, right? So here is the whole of this plate, which is 3,000 or 4,000 kilometers wide, and then you have this little 100-kilometer plateau going through all this complex dynamics, of course, but the actual subduction zone doesn't really notice. So if you do an experiment in which you try to compute what's going to happen to this, what is the buoyancy balance going to do if I put in some buoyant plateau, then when you think in two dimensions, you don't have the full range of choices available to you. So you might look at the vertical force balance and say, well, this thing is too buoyant to be subducted. It's going to be scraped. It's going to be sort of scraped into the overriding plate and accreted or something like that. Well, in reality, in the model, I get confused about that sometimes. But anyway, what's really happening here is that there is a lot of buoyancy around that's subducting, and a very small part of this system is kind of interrupted. And we should think about how those scales interact with one another, as well as thinking about just the local force balance. So a two-dimensional version of this problem would have this plateau be the full width of the subduction zone. If you think of the cross-sectional cartoon, it would be something the full width. You have no choice but either to subduct the thing or break off the slab. Right? So you really have to do that. In here, you get some intermediate behavior. Okay. All right, so I'm going to show a bunch of those models. So now you've got sort of your eye in as to what they're about. I can show you what's underneath those models. There's a sort of, they are actually a little bit like the analog models people do in tanks full of syrup with some sort of putty as the plates, but they're done numerically, and so with the numerical models we have the possibility for a sort of a little bit better mapping between what we think of as the sort of the age of the lithosphere and the rheology and the buoyancy gradients. But because of numerical resolution issues, we still stuck with the idea of this sort of layers of putty and fixed all those rather than trying to solve for a full thermal mechanical model, which is I think you guys will be more familiar with as part of the setup. So it allows us to set up some components of the buoyancy system quite precisely, and then sort of turn off diffusion to allow the to essentially sort of kind of allow the system to have pretty sort of easily predictable equilibrium. And so here's another movie showing a slightly larger buoyancy anomaly, and we can start to see that the behavior can be quite interesting in different parts of this subduction zone. So on the far side here, barely detectable change to the system as a result of essentially the accretion of this buoyant blob. But we can see how that blob gets from the downgoing plate to the overriding plate. First of all, it's sort of essentially indented as a collision. A slab window has formed as part of that process, and then we can watch as the subduction zone picks itself back up again and gets back on track. So at some point you go from straight trench, sort of localized indentation of this collision, and then back. So the subduction zone essentially jumps back. So in cross-section, it really does look like what people have drawn of a slab break-off event followed by subduction restarting. But the dynamics of that is a little bit, doesn't really involve subduction restarting. It's simply propagating sideways from where it was going along the whole time quite happily. There's some buckling and folding of the downgoing plate, which occurs regardless of whether this collision occurs. So if you want to try and do the analysis, you need to kind of look at what that essentially time dependence would be in the absence of this collision, and start doing some relative behavior compared to that. So the sort of standard behavior is essentially sort of a slowly retreating trench with a little bit of buckling on the 670 here, and we would look at the variations to that as a result of this collision. What happens when you have larger and larger objects colliding? Well, as you go a little bit larger, it's much the same, but you start to see when you indent something that's really substantially large, that there's a serious kind of need to consider the deformation and sort of escape of the overriding plate into which this object is being accreted. And here's a sort of a super close-up view of a similar collision. This one is a sort of a ribbon, if you like, coming in sideways. So you'd expect this to be actually a bit more two-dimensional, right? Because this is a nice long, thin object hitting the subduction zone. In actual fact, this creates a very large sort of opportunity for a slab window, which takes some time to develop. and this gigantic sort of rollback sequence around here, which is extremely oblique subduction at certain points, and and a very long subduction zone all of a sudden without really doing it. So depending on the age of the slab and therefore its strength, depends on how fast the window forms and whether or not you get some sort of remnant pieces lying around that you can deal with. But it doesn't affect much. The overriding plate is still undergoing the same sort of kind of like escape mechanism as stuff is being forced out along these shear bands and around the side of the indenting thing. The genuinely non-traditional aspect of this is what happens to this part of the system. When you look at, here's the sort of collision and stuff coming out around the side. Here is extremely extended material, and we don't have a model to sort of put anything back in its place. But the foundering of this slab into the the sort of dramatic rollback over here. There's no possibility of rollback here. It's welded. So so in order to accommodate this is the geometrical sort of dance that the subduction zone goes through, and that the continual indentation here is driven. Since this sits, I didn't say this, but the entire system is only driven by buoyancy. No one's pushing anything. So in order for this collision to continue, you have to keep subducting additional buoyancy. There is no choice, otherwise it's going to stop. So roll back over here, advance over here, and then something very sort of unusual going on in between, where you have sort of a foundering of the subduction zone. And actually, if you look at it, you've got kind of slabs from both directions in a way. So we can look at this profile from A to A prime or something there, somewhat backwards here. And this is as a function of time, so this is how those, how the profiles of, what the sort of subduction trajectories look like. So they're very steep, very much like typical rollback trajectories. So an individual particle in that system is just dropping vertically, okay? But when orchestrated like in this fashion, you're actually, essentially the faint dots here are the position of the lithosphere within this system at any given time. It's formed essentially a hanging loop that is just dropping out, and obviously it's producing that shape. So we end up with this very, we're shortening the margin in this direction, so there's an overall shortening direction here and a bending of any particular path that you see. So this is interesting, but it's we are interested in thinking about this because where are there places where you see these kind of interesting, peculiar shaped subduction systems? And one of them is probably what's going on to the north here, where you have a very arcuate subduction zone, and it's the product of multiple collisions between what might be a simple subduction system and a lot of incoming buoyancy. And the seismicity in here is indicative that you really do have these complicated looking slab geometries. But the evolution of that is still mysterious. I'm not going to try and pull this up in real time, but I'll do that. So in the interest of time, I'm not going to talk about sort of the benchmarking of this process and how it started. We spent a lot of time looking at the Southeast Australian potentially accretion of the Selwyn block as being a sort of a historical example of exactly this process, collision associated with a strong orocline. And people have been chasing this and trying to find evidence for it. Well, the work of Ross Cayley and others has been to sort of map the surface geology and potential fields to see this sort of oroclinal fabric and relate it to these collisions, which is where we started working together. But Nick Rawlinson has been working closely with that group as well, looking at seismic, so sort of fabric in the lithosphere itself from seismic anisotropy, and in another paper with this group, there's the potential to image the indenting blocks in seismic tomography as well. Okay, so how should we be thinking about this? Well, one of the things to think about is that when you try to piece together what's happened somewhere, it's useful to realize, I think, that the indentation of one part of the system is related to the rollback of another, right? So you would expect advance and retreat of a subduction system to be paired and consequential. There's not a coincidence that significant indentation of a margin is associated with escape and rollback elsewhere in that same margin. So it's not indicative that there are multiple processes going on. It should be part of one and the same process. It's in one G-plate reconstruction, so I shouldn't dwell on this. But I guess my point about some of this, since Robert Hall may well be watching, it was not actually to pick one or other reconstruction, but to talk and to raise the question, which I don't know the answer to, what is the appropriate null hypothesis if you're trying to do a reconstruction with a highly, with a complicated-looking subduction system like that, and I guess my point about it is that where you have something being subducted, some sort of collision, some sort of complexity in the continental, in the subduction system with indentation and accretion, you shouldn't imagine that the complicated geometry of the subduction zone is, the null hypothesis should be actually that it might have been straight before that, not that the curves and everything in the system were already there. So I guess that's not really. So I don't know what assumptions you might make, right? But presumably working from the other direction, I don't want to introduce any changes that might not, I can't justify. But from the dynamics part of this story, it works the other way around. It's like, well, these things tend to become straight unless you give them a reason not to be. So I'm going to sort of stop with that point. We can freely discuss it, but I commend you the idea of combining the dynamics of subduction and the whole process of sort of reconstruction and comprehension of the ancient record.
Questions?
Wonderful stuff. Did you try subducting a long, thin body, but in the opposite, sort of 90 degrees to the one you showed? So something like a seamount chain, maybe, where you've got.
Yeah, we did. We started off doing that, and I haven't gone back and done this more precisely. But almost all the models have something. I mean, they still have this kind of coupled advanced retreat, which is sort of fundamental to the dynamics of the system as it's set up here. So, well, maybe what I can say is one of the things we did was that we've got the box has walls, right, and so the direction at which the overall subduction, the plate velocity, if you like, of this guy is constrained. It can only go this way. So if something interrupts the subduction zone, rather than changing the configuration of the plates, it changes the configuration of the trench. And that's kind of convenient for isolating some of the dynamics, but that's not fundamental to the way this is set up. The possibility of other degrees of freedom, like something rotating, is still there. We just haven't really studied that in detail. But still, basically that sort of coupling of the advance and retreat occurs almost independent of the shape of the thing that we're forcing in. It's just how much time that takes relative to forming a slab window versus rollback versus all sorts of things, I think. Just Frenchman gets to know Frenchman.
I thought you said buoyancy was the only driving force. Is that right?
In these models, yes, that's right.
So you only get drag from the subducting plate, no push from the ridge.
There is some push from the ridge because you have a buoyancy gradient at that end as well. So there is effectively, out here, there is a contrast between the stuff that is a little bit more dense and the material that's next to it. But so that there is, but there's no. What's missing from this is kind of a gradient of in the density of the material. So no lithospheric thickness changing as a function of age, which would provide sort of, rather than a buoyancy force at one end, would provide a sort of smoothly varying buoyancy body force, if you like. So it's not just the downgoing thing pulling. There is this there is a push from the back, but it's buoyancy driven. So if you do choke the subduction zone enough, something else will happen.
Cheers.
Okay, yeah. So why these little blocks, do not subduct? Is it a problem of buoyancy or is it a problem of coupling?
It's a bit of both, I think.
So how sensitive it is to the decoupling if you allow the development of the zone of decoupling along the subduction zone, does this help the subduction of those blocks? After all, India has subducted underneath Asia.
That's right, and I know that, but I was going to show you the. Okay, so although I don't have an answer to the details of the coupling part of that, the difference between these are models we did for a completely different purpose, but they have buoyancy underneath the plate or on top, and as a side effect of where you put the buoyancy anomaly, not only just the size, there's a size question as well, but if you put the buoyancy anomaly at the top of the plate, then of course it chokes the subduction zone right there, and you see what I just showed you basically. You put it underneath, then actually the upper plate and lower plate aren't quite weakly coupled, and so you get quite a significant period of, in this case, flat slab subduction because it's still able to push underneath. But you can tell how weakly coupled it is because the trench doesn't move at all. And so those are two extremes, actually, of this problem. So I think the coupling actually turns out to be very important. If you put the two together, then it just destroys everything.
So if there are no further questions, I think we should thank Louis for our talk. It probably deserves some more discussion in terms of how we actually make these different approaches converge eventually, which is not obvious to me at all at the moment, and at least not in the near future. So our next speaker is Simon.